Okay, here we go, starting the second portion of this course, Chem 230, Introduction to Organic Chemistry at Glendale Community College. And this next section is all going to be focused on acidity. And because of the way our book is organized, in order to cover the various factors that influence acidity of compounds, we've got a smattering of chapters. Chapters 2, 5, and 7 all have some important information about acidity and definitions of acidity and different compounds that are acidic and why they're acidic, especially the factors that affect pKa. They're going to be spread throughout different chapters. So here's a little reading assignment to get us up to speed with respect to acidity. And then we'll also cover acidity through the lecture notes and focus on some of the most important concepts. So the acidity of organic compounds. One very common and very useful definition of an acid is that it's a hydrogen ion donor, so an H plus donor. That doesn't mean that everything with an H in it is going to be an acid, but if something's got a hydrogen atom in it, that hydrogen atom might be predisposed to be donated to something else that wants it more. The Ka of an acid is called its acid dissociation constant, and if you've had a good course in general chemistry before starting this, you have probably gone through what the acid dissociation constant is and calculated the concentration of hydrogen ions in various solutions of weak and strong acids based on acid dissociation constants. In this course, we're more in an introductory level. And so we're just basically going to say that the higher the Ka, the stronger or more acidic. So in lines with the grammar of this sentence, the more acidic a compound is would make sense. And then pKa is a mathematical concept. The acid dissociation constants cover such a range that it's more useful to think of a log scale. So pKa is minus log of the Ka. Just like pH is minus log of the hydrogen ion concentration, the mathematical function negative log is the p part, negative log of Ka is pKa. The lower the pKa you have, the more acidic. So because of this negative sign, the higher the Ka, the lower the pKa. And so that's going to be really important for us to understand, because we're going to tabulate things based on pKas rather than Kas. Alright, so each acid has a conjugate base is another idea. We're going to try to link the reactivity of an acid to its conjugate base and to think about reactions that acids undergo, whereas the product of the acid reacting is going to be the conjugate base. And a very key relationship here for us to understand is that the more reactive an acid is, the more stable its conjugate base is. So if an acid really wants to give up an H+, then the part of the acid that becomes the conjugate base does not want the H+ back. So that's something that I can summarize with an example. Hydrochloric acid is a very strong acid. Most people know it fully dissociates in water. And I'm going to write this sort of in its most simple form. A hydrogen ion that's surrounded by waters is formed. And then the conjugate base is the chloride. So with the H+, this is an acid. When it loses the H+, it becomes the conjugate base. So to find the conjugate base of any acid, you just remove the H+ and see what you're left with. Now, if this is very strong, the reason that this can give up an H+ is because the chloride doesn't want it very much. It gives up the H+, and to something else usually, like the water. And then the chloride that's formed does not want to grab this back. So you might draw this with little sort of more like equilibrium arrows, where this reaction forward is very favorable, this reaction backwards is not so favorable. So if this is a strong acid, its conjugate is a very weak and unreactive base. So potentially this chloride could grab an H+, and you might think it would do so because it's negatively charged. It might like the H+, but unfortunately the negative charge here is distributed in such a way it's not so available to the H+, and these really aren't as attracted to each other as you might think based on their charges. So a couple of key ideas. An acid is an H+ donor. That's the definition we're going to use through this part of the course. The Ka of an acid is its acid dissociation constant. The higher the Ka, the more acidic a compound is. pKa is the negative log of Ka, so that means the lower the pKa, the more acidic a compound is going to be. And then each acid has a conjugate base. The more reactive the acid is, the more stable its conjugate base is. And that's what I mean by a weak conjugate base is stable and unreactive. And the converse is also true. If you have something that's a very weak base, like NH3, if you have something that's a weak acid, so ammonia is a very weak acid. If that gave up an H+, you'd have an NH2- left over as its conjugate base. And then because this is a very weak acid, this is going to be a very strong conjugate base. So it's very difficult to remove the H+ from the ammonia, because the thing that's created, the NH2- wants to grab this back, so the reverse reaction is much more efficient. The strong conjugate base wants to grab the H+ and form the ammonia. For it to give up the H+, very rarely will happen, because this wants to hold on to it so much. So, little introduction and some definitions, and then we're going to get into some factors that affect acidity for different compounds. And different books, different instructors will characterize and list factors differently. I have my own way of doing it, which I think is very useful for predicting acidity of compounds.